Let me start recording. Okay, hello everyone. We're very happy to have Andrea here today to tell us something about Ferrari connections for 2D 2,2 theories and generalized cohomology theories. Feel free to start.
Yes, so thank you very much for the invitation. It's great to speak at Virginia Tech. I noticed a while ago that I was actually born 60 kilometers from a venue of Virginia Tech. So it's kind of feels a little bit to be at home. So the title of my talk has been already mentioned. It's Berry connections for 2D theories and generalized cohomology theories. And I hope to report on some set of ideas and the first chapter of a set of ideas that I am developing with my collaborator, Daniel Chang, who's here in the audience, whose aim is indeed to try to connect Berry connections and generalized cohomologies more broadly. So this is a brief outline of my talk. I'm gonna start by mentioning a few aspects of supersymmetric quantum field theories and connection to cohomology theories, just to give a little bit of background. And then I'm going to move to discuss the setup, the main setup that this talk is going to be about, like which kind of theories we're considering, which kind of Berry connections, and so on and so forth. And I will then move to discuss two different kinds of spectral data for these Berry connections that I claim are kind of related to different kinds of cohomology theories or generalized cohomology theories. And I will end with some conclusions and further directions. So let me begin by saying some broad facts about supersymmetric quantum field theory and cohomology theory, just to frame the problem. So for supersymmetric quantum field theory that flow to a sigma model with some maybe smooth or more compact target X, it has long been known, at least since we can work on supersymmetric quantum mechanics and Morse theory, that local operators in Q cohomology for some operator Q in the supersymmetry algebra that is nilpotent can sometimes be mapped to some geometric data encoding some data related to X. And in particular, sometimes the cohomology of the Q of this Q operator becomes some cohomology theory for X. So for instance, if we take an N=4 supersymmetric quantum mechanics, which such a target, we have an operator that if we anti-commute it with the adjoint, we get the Hamiltonian. And if we look at the Q cohomology of this operator, which sometimes is equivalent to the supersymmetric ground states of this system, if you look at this cohomology, sometimes it's going to be the same as the drum cohomology of X. So of relevance today are going to be two-dimensional systems. In particular, I'm going to focus on two-dimensional 2,2 theories with some flavor symmetry. Now, by a long series of work, and this is a fact that has been studied quite extensively, if we take the supercharged Q, which is the A-type supercharge, local operators in its cohomology form a ring, the chiral ring, and this chiral ring is mapped to is expected to be isomorphic to the quantum equivariant cohomology of X, where the equivariance is taken with respect to this flavor. It's the same as this torus action. For example, if you have never seen what quantum equivalent cohomology is, I don't think that for this audience is the case. But if we consider the standard cohomology of Pn, say the complex projective space, then its cohomology is generated by some operator sigma in degree 2, subject to some relation. This sigma is basically the first-gen class of O minus 1, and if you multiply it sufficient number of times, it becomes 0. Now, this statement can be corrected a little bit in the realm of quantum cohomology, where you have a quantum parameter Q, which physically, as we're going to see, is related to the Fi parameter of the theory. And now, if we start multiplying this operator, instead of getting 0, we get Q, and this correction is related to some path integral computations in physics that arise from considering correlator functions between three operators, and geometrically are related to counts of a higher degree holomorphic curves, where Q counts the degree of the curves. So this can be promoted to an equivariant version. We have a n-1 action on Pn, and we can basically deform the ring by the equivariant parameters, so that when we specify this equivariant parameter to 0, we get back the original quantum cohomology. And this equivariant quantum cohomology is going to be one of the main gadgets that we are going to discuss today. So in fact, there is an important result which I'm going to make use of, and it is that one can consider an effective, for such a 2D theory, one can consider the effective theory on its Coulomb branch. And it's known that the quantum equivariant cohomology ring relations can be extracted from the so-called beta equation that determine the vacuum of the theory. And in particular, you can write them as this expression here, e to the derivative of an effective twisted superpotential, which basically describes the effective theory on the Coulomb branch. And here again, the sigmas are the maybe I failed to mention it earlier, but sigma are the bottom components of vector multiplet scalars, and m's are bottom components of background vector multiplets for flavor symmetries. So as an example, we can take super QED, let's say n+1, which is a 2D 1 to 2 theory with n+1 chiral multiplets, the mistake, in the fundamental representation. It flows to a sigma model to Pn, and we can write, since we have only one gauge group, we are only one sigma, and we can write its effective superpotential like this. And this model flows to a sigma model with target Pn, and if we compute the beta equations I wrote up in this slide, we indeed find the same relations that I wrote down before, where this little tau is the Fi parameter of the theory, and it's related to the quantum deformation parameter that I wrote here. Now, more recently, and there have been a few papers, one by my collaborator Ben Shang and Matthew Pullimore, another one by Dedushenko and Nekrasov, where there have been attempts to extract so-called generalized cohomology theories from Berry connections. Now, if you have not heard what a Berry connection is, I'm going to make a few comments right now. Essentially, suppose that we have a system, a physical system, or let's say even a quantum mechanical system that has some so-called deformation parameters. This can be values of background of masses in background vector multiplets in supersymmetric theories. And in particular, the Hamiltonian is going to depend on these parameters. And so we can consider, amongst other things, the bundle of supersymmetric ground states, the states of zero energy with respect to the Hamiltonian, fibering over the space of deformations. Now, if we take a little loop in this space, we may go back to the same M, but we could, in principle, pick up a phase, which is called the Berry phase, and which phase we pick up is going to be prescribed by a unitary connection on the space of deformations. And one way of defining what this Berry connection is simply you take a basis for your space of supersymmetric ground states depending on M, and you can compute the dot product of two states by with a derivative of M inserted. This is a connection that tells you how phases change as you move adiabatically in the space of deformations. Now, this connection to generalized cohomology theory has been worked out for what is known as equivariant elliptic cohomology, starting from a three-dimensional theory on a space-time which has the form R times an elliptic curve. However, it can be done for other generalized cohomology theories, and we, for instance, elaborated upon one example in our recent paper. This example is the complex K theory of X. You can obtain this starting from a 2D theory, which is the main subject of this talk. On the geometry R times a circle. Now, if you don't know what a generalized cohomology theory is, this is not going to be very important for now. One thing that you can keep in mind is that if you think functorially, like as a cohomology theory assigning some algebraic object to some space, then it's basically like a cohomology theory, but the dimension axiom, meaning that all things attached to points are concentrated in degree 0 might fail. And in fact, complex K theory, which is, as I'm going to discuss later, the theory of complex vector bundle on a space, essentially, assigns to a point simply the space of functions on a torus. So, yeah, so my goal for today is indeed to demonstrate that Berry connections encode aspects of different kinds of generalized cohomology theories, and in particular for our main focus, which is a 2D to 2 theory on a cylinder with a flavor symmetry T that flows to a nonlinear sigma model with target X. We have that if we look at the geometry of the Berry connections, we study this Berry connection, then we are able to encode them into different kinds of so-called spectral data for them, which are basically ways of parametrizing Berry connections. And one kind of spectral data is going to be related to the quantum equivariant cohomology of X, and the second kind of spectral data is going to be related to the equivariant K theory of X. So for technical reasons, I will assume that my theory T has isolated massive vacua, and that the target is equivariantly formal, or GKM. Some of these assumptions can probably be lifted, and a good example to keep in mind is simply Pn, as I have discussed previously.
So let me interrupt with a quick dumb question, just to make certain I'm tracking you correctly. When I think about, I'm familiar with quantum K theory computations in GLSMs, where you start with with what's effectively a 3D theory, do some close line reduction to along a circle to construct some effective low energy 2D theory.
Yeah.
Is that what you're talking about, or are you talking about something else? And the thing that's sort of slightly confusing me is you're talking about quantum K theory from 2D theories. I guess we're going to find out whether it's
yeah, Eric, you're going to find out. So like the quantum K theory would be a lift to 3 dimensions indeed of this Q of this of the quantum cohomology side.
Okay,
and
good.
The fact that you're seeing the K theory here, I'm going to explain it a little bit, but it's because you have a circle. And there is this law that the complex equivariant K theory of a space is related to the cohomology of its loop space. So if you look effectively on R, you may be able to extract, you may hope to be able to extract complex K-theory data if you are on this kind of geometry. Yes, I hope I answered your question.
That helps. All right, thanks.
Yeah, thanks. All right, so let me talk about the setup. So as I've just said, we can consider a theory T with, for simplicity, I'm going to say rank 1 abelian flavor symmetry. And I'm going to put this theory on a cylinder. And the cylinder, or the circumference of the cylinder, is going to be of order L, let's say. And for this theory, which has this flavor symmetry, we can turn on different kinds of deformation parameters. So we can turn on a complex twisted mass, for instance, which is, again, related to bottom components of vector multiplets. But we can also turn on a holonomy for this symmetry here around DS1. And so if in this sort of situation on a cylinder, the space of deformation parameters is going to be simply S1 times R2, where in the first instance, R2 is parameterized by W, and the S1 is parameterized by the holonomy. And so today we're going to work a lot on with this space of deformation parameters, which is like R3 with quotiented by a Z action that brings it down to S1 times R2. So if we let H be the Hamiltonian for the evolution along the cylinder, we can define what the ground states of the theory are, meaning I'm gonna, what the ground states, supersymmetric ground states I'm gonna talk about are simply the ground states for the effective supersymmetric quantum mechanics along this R. And as I have introduced in the previous section, these ground states in general depend on my space of deformation. So they may depend on this mass and they may depend on this holonomy. So when I build supersymmetric ground states, I'm gonna get some bundle on R2 times S1. Now the bundle, if its rank is 1, will be endowed with a UN, a unitary connection, which is the Berry connection, and a Higgs field, which roughly speaking is the quantized flavor moment map. And these two things together, it's known from a series of work of Cecotti-Vafa, Cecotti-Gautav-Vafa, and for supersymmetric quantum mechanics, Tong and collaborators, that in order to preserve supersymmetry and to be a genuine Berry connection for a 2D2 theory, they must satisfy some equations, which are the Cohomology equations. And in particular, you can decompose the Cohomology equations like this, and get a so-called complex equation, which is the top one, and the real equation, which is the bottom one. But so just to summarize, we have the space of supersymmetric ground states fibered over M, and it's endowed naturally with a connection determined by the theory that satisfies the Cohomology equations. Now, asymptotically, as we make the mass very large, we can prove a few facts that are of relevance later. So the bundle of supersymmetric ground states has a smooth spectral bundle, which split into a sum of line bundles labeled by the isolated massive vacua of the theory. Moreover, the combination AT plus I5, where AT is the connection in the compactified directions, in the circle direction, can be computed at its vacuum in terms of the effective twisted superpotential evaluated at vacuum alpha. And if you go through some equations, you get some equations like this, where asymptotically the Berry connection in this complexified connection in the circle direction becomes related to the effective with the superpotential. So these facts imply that the monopoles that come out from physical theories are also called Cherkis-Kapustin type. And in particular, they tend to copies of Dirac monopoles at very large mass, and which are basically arise from description of defective theories around these isolated massive vacua. Now, there was some work in mathematics due to Mochizuki a few years ago, I think 4 or 5 years ago, where his main goal was to try to encode solutions to periodic monopoles, which are basically solutions to the Cohomology equations on this geometry. And in order to encode these solutions, introduced a P1 family of mini complex structures on our space M, which I recall this S1 times R2. In particular, you might want to slice your space-time in a different way, introducing a real parameter T naught and a complex parameter beta naught. And so effectively what you want to say is that your space is looks locally like R times C, where you have a holomorphic structure on C. Now, there are some further conditions to be satisfied, but this is the basic idea. And so locally, you can parameterize or coordinatize your space as T naught and beta naught, where T naught is a real parameter and B naught a complex one. And there is a whole space of these so-called mini complex structures. It's a P1 space. And intuitively, for the following, it's very useful to keep in mind that at lambda equals to 0, which reduces to our previous case, where we simply have T and W, we identify points in R times C2 that are located at the same point in C. But in a different so-called mini complex structure, what happens is that you are quotienting R3 in a way that conflicts a little bit with talking about real and holomorphic directions, and you might be identifying points that differ and in the C direction. So in particular, at lambda equals to 0, if you are identifying points that lie at the same that share the same complex coordinate, as a mini complex manifold, M is going to be like a circle times complex mass, so times the space parameter of the complex mass, which is the C. But for instance, if the modulus of lambda is 1, you get a totally different space where you can take the real direction and the periodic one to build a C star where a complex structure lives, and you're left with another real direction, which is, however, R.
Just so I'm following, sorry to interrupt, just so I'm following this
Yes.
completely. You've got this 3-manifold M, you foliated it. Are you always going to foliate it along the holonomies? So is the T direction always going to be the one that's going to parameterize the different complex spaces, or are you going to allow for mixings? Given R3, I can imagine foliating it in lots of directions. But given the examples there, am I correct in thinking that the parameter, the extra direction that you're going to factor out is always going to be the direction corresponding to holonomies?
No, the holonomy only at lambda equals to 0. The real direction is the holonomy direction, and then you have a proper foliation. Okay. But otherwise, as you can see in this equation here, T is the holonomy, W is the mass. You're gonna get some mixing. Okay. And so when you what you call the real direction might not be the holonomy, and this means very concretely that when you start traveling in what you're now parameterizing as the real direction, to go back to the same points, you need to shift also the complex one because there is some mixing. So it's no longer a foliation. Okay. All right. Thanks. Okay. Thank you. So more physically, what we can consider is with the analog physically of what I've just said is that there is a P1 family of supercharges, which looks like this. And at lambda equals to 0, we have the standard QA supercharge. And when the modulus of lambda is 1, we have another kind of supercharge that squares to rotations of the circle. And this family has the feature that they are all supercharges for a for two quantum mechanics on along the real direction of the cylinder. And they interpolate between the QA supercharge and this other supercharge. And here, for your convenience, I've just reported some of the, the non-trivial supersymmetry algebra relations, and you can see that at lambda modulus of lambda equals 1 in particular, we are going to have some. Q lambda is going to square to rotations. JT is simply the generator of flavor symmetries, and we can pair it with our parameters in this way, and they appear as central charges in the supersymmetry algebra as expected. So now, given a space that has the structure I said before, like it looks a little bit like R times C, if you have a bundle on it, which is the bundle of supersymmetric ground states, we can define something which is called a mini-holomorphic structure. So for the purpose of this talk, and it's basically the essence of this notion, is that if you restrict your bundle to a fixed real value, you get a Dolbeau operator. And the Dolbeau operator is going to be d beta naught bar. And moreover, the Cohomology equations that I wrote down before that need to be satisfied by a Berry connection imply that the Dolbeau operator and a complexified connection in the real direction commute. And the first observation, perhaps, in my paper with Dan, is that if we define this complexified connection and the Dolbeau operator, then these operators descend to Q lambda cohomology, meaning that they commute with the Q lambda supercharge. Recall that T naught and beta naught were themselves depending on lambda, and for that given lambda, at that given lambda, these operators become or descend, act in a well-defined way in Q lambda cohomology. So, in particular, this means that the supersymmetric ground states viewed as states in Q lambda cohomology have the structure of a mini-holomorphic bundle at that given that is assigned to that given mini complex structure on N. Okay, and here was enough for the setup, and I should stop to ask whether there are any questions.
I think it's good so far.
Yeah, okay. If not, I'm gonna proceed. And so, as I said, so from a theory, we can try to extract. We know that we're gonna get a Berry connection that's gonna be some periodic monopole. One question you may ask is, how do I parameterize the possible periodic monopoles in general? And this is going to be the first. There are two ways I claim to do it, and or at least that mathematicians have dreamed so far. And so I'll start with the first one. So let me first set lambda equals to 0. This is the space that Eric was remarking. It's foliated in this following way. We have an S1, and we have a complex, a copy of C. Now, let me define a bit naively to V to be the space of holomorphic sections of the bundle of the space of holomorphic sections of the bundle which is obtained from the supersymmetric ground state by restricting it at 0. As I told you before, we're going to get a Dolbeau operator, which is basically dw bar. And so I can define the space of holomorphic sections at 0. I also told you before that this complexified connection and the Dolbeau operator commute. This means that I can parallel transport the sections around the real direction by preserving holomorphicity of the sections, by preserving the holomorphic structure on the bundle. However, if I do a full loop around the S1, I'm going to go back to the same point. So remember that I was saying this S1 excites L. So if I start from E0 and I go to EL, I'm going to get a CW linear automorphism of the space of holomorphic sections. Here, CW is basically the ring of rational functions in W. The fact that it's rational functions because I should perhaps say meromorphic rather than holomorphic, but because the monopoles can have Dirac type singularity at various points, but I'm gonna skip these technical details for now, just to give you an intuition of what is going on. So by parallel transporting the space of sections around the S1, I'm gonna get a CW linear automorphism of this space V, which is a CW module V. So formally, if I do this, I get a pair of a CW module and a CW linear automorphism. And this pair is what is known as a zero difference CW module, aka CW module with CW linear action on it. And one of the, in this remarkable piece of work, Mochizuki basically proved that there is a one-to-one correspondence between stable, parabolic, and other adjectives difference modules and periodic Cherkis-Kapustin monopoles. So basically, if you take a monopole and perform this game, you're going to get back module V and an automorphism for it F. And if you keep track of a sufficient amount of data, then you can basically encode uniquely the monopole it came from. One can, moreover, extract from these modules a so-called spectral curve. So we can basically look at the space PW in C star times C, and look at basically the eigenvalues of this automorphism. And the eigenvalues are going to span a Lagrangian subvariety of C star times C, where the symplectic form is the standard one for C star times C. And one of the observations in my paper with Dan is that suppose that P flows to a nonlinear sigma model with some GKM target X, then the spectral curve, which is called the Cherkis-Kapustin spectral curve for the very connection of the theory, is basically what a physicist could call the momentum space representation for the spectrum of the quantum equivariant cohomology of X. This is not too surprising because at lambda equals 0, recall that the supercharging I was using to put this mini holomorphic structure on the bundle is precisely the QA supercharge, which computes the quantum equivariant cohomology. But more precisely, what one ought to say, and this is also part of some work in progress based on work of Telemann, is that these operators P and W, one that basically gives me it's related to the eigenvalues of the automorphism. They end up forming a 3D pure gauge theory Coulomb branch algebra, and this algebra acts on the equivariant quantum cohomology. And basically, a spectral curve of the monopole, what we've done is we have identified it with what is basically the support of the corresponding sheaf that you can build on this Lagrangian in the Coulomb branch algebra. But for the purpose of this talk, I think it's good simply to keep in mind that we have some representation of the quantum equivariant cohomology and of its spectrum, which is related to the data of the Berry connection. So let me briefly try to tell you why. So the intuitive argument is that if you try to compute this the holonomy around the S1, the relevant operator that you see that should act in the part integral is basically of the form e to the second equation I wrote here, e to the w effective over dw. And moreover, you can compute the eigenvalues by doing a trick and going at values of very large radius, aka basically R2, where the ground states, the generator, are in correspondence with the massive vacuum of the theory. And then you can try to evaluate the operator that basically parallel transports you around S1 at this vacuum. And so if you do this, so basically go to flat space, try to describe the bundle in terms of the massive vacuum of the theory, and then try to compute what the holonomy is, you get these two set of equations. And so we have simultaneous equations that are simultaneous solutions to the equations e to the dw effective over the sigma. For each sigma we have is 1, and e to the dw effective over the dw is p. And you can view the second equation intuitively as basically a change of variable for p. I go from w to p. And so in this case, in this sense, these relations that define the spectral curve are momentum space representations for the quantum equivariant cohomology. So let me go through an example just to make things a little clearer. I had introduced already a few elements of what we needed, so I'm going to be rather quick. So in the super QED2 example, we had so we know that this flows to a nonlinear sigma model with target P1. And for rescaling of the mass W, the vacuum equations, beta equations look like this. They're basically the quantum equivariant cohomology of P1. And then we have this equation that kind of performs a change of variable. And if we join them, if we basically substitute for sigma in here, we get a quadratic equation like this, or we can decompose it as the bottom of this slide, which tell us what the eigenvalues of the holonomy are. And if you compute this, you discover that for super QED2, the relevant monopole associated to the Berry connection is azimuth SU2 monopole. And you can very concretely compare that the spectral curve you get is the spectral curve for an SU2 monopole. So this was our first computation of Berry connections, starting from a theory, and in particular, linking it to some geometric data of the model.
So, sorry, let me ask a dumb question just to make certain I'm keeping up. So my understanding from the previous transparency was that, or one of the previous transparencies, was the spectral curve should be identified with spec of the equivariant quantum cohomology. So in the case of P1 there, you know, if there were no equivariant parameters, then that spec should just be 2 points. It's just the spec of the ring Cx mod x squared minus q. If you add in equivariant parameters, then it's clear you get some families, basically a family where the fibers are a couple of points moving around. So then from that perspective, what's the P doing there? Is that curve at the bottom again spec of that equivariant quantum cohomology ring? So M is okay. M is clearly the twisted mass. It's the equivariant parameter. But then where does the P show up? So I guess maybe I can sort of answer my own question. Sorry, you've got the equation above, which gives P squared. And then I guess what you're going to tell me is if I solve for P and just plug it in, then I'm going to get a curve that is spec of. Okay, sorry, I'm just being slow this afternoon. I think I answered my own question.
Yeah, I think you did. Yes, that's correct. It sounded correct. Yes. Okay.
Okay, great. Sorry to interrupt. Please continue.
No. Yes. Okay, so for now we have restricted ourselves to lambda equals to 0, but more interesting stuff happens when we take another lambda. So recall that we were considering a P1 worth of supercharges, and these supercharges induce some mini holomorphic structures on the space of supersymmetric ground states. So we are free to consider to view the space of supersymmetric ground states as the states in the cohomology of some other supercharge, and define another space of holomorphic sections that now are taken with respect to another minimum holomorphic structure. So here the Dolbeault differential is slightly different. We still define E naught to be E at T naught, equals to 0. Our Dolbeault differential is going to be nabla beta bar naught. But the crucial lemma, let's call it like this, that we had before, that nabla theta naught, T naught, and nabla and the Dolbeault operator commute still holds, as I have said in a previous transparency. And so we can still consider F, for an abuse of notation, I'm going to use the same letter, as the parallel transport along T naught. And we are still free to parallel transport our holomorphic sections that we defined at T naught. But there is a catch. It's the catch that I highlighted in a discussion with Eric previously. It's that at lambda different from 0, when you travel in the real direction, you do not really go back to the same point, but you do so if you do a shift in the complex plane. And excuse me, yes. So here, if I define this phi star to be the pullback of beta naught, I basically shift it by 2I lambda L. Then if I parallel transport my sections and do this pullback here, I do go back to precisely to a bundle which is isomorphic to the bundle I started with. And so what I get in this case is no longer a 0 difference module as I had before, but 2 lambda I, and L is the side of the circle, but you can kind of normalize it away, difference C beta naught module. So this simply means that if I have some rational function of beta naught that multiplies a section, and I evaluate my, and I act with my automorphism, I need to remember that I need to pull back this rational function as well when I pass through F. And so in this way, simply by looking at the cohomology of some other supercharge, we can extract from the space of or the bundle of supersymmetric ground states a difference module for any particular from Berry connection. We can extract a difference module. And in fact, Mochizuki proves something along the following lines, that there is still a one-to-one correspondence between suitable 2I lambda difference modules and Cherkis-Kapustin monopoles. I just want to say that this result is quite deep and subtle, and it's the culmination of probably decades of work on Ichi Kobayashi-style correspondences for monopoles. The modules will still be endowed with some extra structure that I've not talked about, that keeps track of location of the monopole singularities, as well as asymptotic behavior at infinity. And conditions at infinity in particular require some adjustments to the mini-complex chart. This is not too relevant for my discussion, but I simply want to emphasize that this correspondence here has been established very rigorously in mathematics, and we can just rely on it. But physically, let us try to relate these things to some physical data. So if we impose some boundary condition on our cylinder that actually preserves the supercharged Q lambda, then the path integral is going to generate a state that formally generate a state D. Now, people who are a little familiar with the branes and so on and so forth know that these states here may be non-normalizable, and they're also kind of difficult to compute. So it's not necessarily a well-defined normalizable ground states and therefore an element of E. However, by some TT star geometry, we know, and work in particular work of Horik, Vafa, we know that it must generate a flat sections of the Lux connection of the theory, and this implies, in particular, something that Dan and I checked, that this state D is annihilated by the nabla T naught, and what was our Dolbeault operator at fixed value of T naught. Therefore, we expect that if we are able to generate such a state and we act with the automorphism on the state, we get back the same. This is simply because it's already automatically parallel transported around T naught. So in our paper, we claim that this implies some difference equations for so-called brane amplitudes. So what we do is that we formally take these states for fixed value of T naught in some, and we decompose it in some lambda or project it down to a basis of the supersymmetric ground states. So you basically pair this state here with partition of unity based, or no, sorry, of the identity based on a basis for the space of supersymmetric ground states that I called A lambda, since it depends on lambda. We can project it down like this, and then from this equation I showed you before, we can conclude or derive an equation of the form that I wrote here at the bottom. So for any basis or holomorphic basis in mini-holomorphic structure lambda, there is an equation where if I shift this brane amplitude here, this pairing between A lambda and D by the operator 2I lambda L, then I get a matrix of rational functions in beta naught times the holomorphic basis B lambda. And this is a difference equation that we have not noticed previously in the literature, and we claim it exists. Moreover, we can show that this matrix difference equation quantizes the spectral curve of the monopole, which I recall is simply those values of P and W's, such that the determinant of P minus FW is 0. In fact, my shift operator P and my operator B naught, they satisfy some quantized relations. If I shift beta naught and if I pass through beta naught with P, I must pick up at Y lambda L. And so they are kind of quantized versions of the operators P, W. And moreover, we prove that we must have, as lambda equals to 0, that the eigenvalues of this matrix G B naught actually satisfy the equations of the classical spectral curve. So why is this? There is some engineering to be done to understand, but we can take a basis A lambda such that in the lambda goes to 0 limit, this reduces to the insertion of a chiral ring operator at the tip of an A-twisted cigar. Remember that at lambda equals to 0, we are working in the standard A-twist, so we can take an A-twisted cigar. And propagating, inserting an operator an A-twisted operator at the tip is going to produce some state, and it's known that we can produce a complete basis for the space of the ground states in this way. And moreover, we can consider some thimble branes, which are labeled by vacuum of the theory, which have a very well-known limiting behavior. And basically combining these two ingredients, we can understand what the shift, there is a spurious one here, for which I apologize, but what this shift operator does to the brane amplitude in the lambda goes to 0 limit. And what we get back is basically what were the eigenvalues I was computing before. So this is all nice at a formal level, meaning that we know that we have derived some difference equations that quantize the spectral curve of the monopole. And we also know that this spectral curve of the monopole is somehow related to the quantum equivariant cohomology of the theory. So we have quantized something related to the quantum equivariant cohomology of the theory. However, it is not super straightforward to check these results directly. And the main issue is that the brane amplitudes here are highly non-BPS objects, and they are difficult to compute. But we don't despair, and we try to find something that we can actually compute with and or compute and play with. And this something is because before taking the lambda goes to 0 limits directly, we can try to go to an intermediate limit that interplays with lambda and the size of the circle, where these brane amplitudes are expected, for various reasons, to degenerate into supersymmetric partition functions on hemispheres. So basically, in this limit, we expect these brane amplitudes to become supersymmetric partition functions on hemispheres where A labels the insertion of a twisted operator in the hemisphere, and epsilon is related to the size of it. And these gadgets here are exactly calculable via localization, and it has been done. And but if we take these limits and look at what happens to our equation, we still get a difference equation for these vortex partition functions. So in particular, if we still have a shift operator P that shifts the M, which is related by rescaling to W. And if we do shift M in these vortex partition functions, we get back some difference. We get to some difference equation that is basically a reduction in the conformal limit of what we had before. So this to us was also new, and at least in the realm of vortex partition functions and hemisphere partition functions. And what is fun is that you can actually check this very explicitly. So let me tell you an example. So we can consider again super QED2 because it's the example we have got accustomed to. And these vortex partition functions, they can be very, hemisphere partition functions, I should say, they can be computed very explicitly. And I put two examples here by some contour integrals and gamma functions. And then if you act with operators that shift M and you arrange things a little bit, you can derive an equation like this one that I've wrote down, which is, for instance, which is obeyed by all of these hemisphere partition functions, and is manifestly a quantization of the curve I wrote down before. So if you take the epsilon goes to 0 limit, you get exactly the same form, and the shift operator becomes P. That's a multiplication by P, and you happily land on the spectral curve for this SU2 monopole that I derived before. So although our arguments for deriving difference equations for brane amplitudes were a little formal, we can at least, there are at least some checks we can make to, in some limits, to show that these things actually exist and are kind of powerful. And so I'm gonna end it here also because I'm running a little late with spectral data 1. But just to summarize, I've tried to tell you that spectral data for periconnections is related to the quantum equivalent cohomology of the target if a theory flows to a nonlinear sigma model with a target. And moreover, we can happily quantize the spectral curve equations for the monopole in an interesting way. And so now there is a whole second chapter that I'm gonna keep a little brief, which I promised you at the beginning that from the Berry connection, we could extract not only things or objects related to the quantum equivariant cohomology, but also objects related to the complex equivariant K-theory of X. And I'm gonna be very brief, but so if we pick a particular supercharge and lambda equals to 1, I mentioned previously that as a so-called mini complex manifold, a manifold that has a real and a holomorphic direction, so to speak, locally, the space of ground states become C star times R. Now, Q lambda is then a supercharge that squares two rotations of the circle S1 on which we are quantizing the theory. And its cohomology is expected to be related to the equivariant complex K-theory of X. Now, under our formal assumptions, the equivariant complex K-theory of X, which we take to be equivariantly formal and GKM, has the following schematic form. This is all you need to know about it. So the spectrum of KTX is basically copies of C stars labeled by the fixed points of X, modulo some gluing conditions on these copies of C star. And you can derive this by some technology that is called the Kirwan surjectivity, that I am, however, not gonna introduce very well because I don't have time. But essentially, what you have to keep in mind is that basically the complex equivariant K-theory of X is a ring that keeps track of complex equivariant bundles on X. And under some assumptions of X, it's possible to encode this ring by taking the complex equivariant K-theory of its fixed points and imposing some gluing relations. Now, the supercharge Q lambda is a dimensional reduction of the supercharge used in these previous papers that I mentioned to extract elliptic cohomology of some variety from the Berry connection. And in this reduction here, let's call it like this, we indeed expect that the equivariant elliptic cohomology reduces to the equivariant complex K-theory of X. So in the paper with Dan, we claim that indeed the same can be done for KTX with 2D theory quantized on a circle, and that this is related to a second kind of spectral data for the Berry connection. Now, let me recall, I will still again consider super QD2 as an example. So we have two vacua and the bundle of supersymmetric ground states at rank 2. And I will denote coordinates on the space of supersymmetry of deformations, C star times R, Z bar, and MR. So what we get in this case is we can study the space of supersymmetric ground states as a holomorphic bundle on C star fibered over R. And the Cohomology equations again imply that we can parallel transport these the holomorphic sections of this bundle in the R direction. So we can consider the limit for as the real direction goes to infinity. And we're going to get a filtration determined of the bundle, determined by the fall-off rate of its holomorphic sections. So there is a line sub-bundle in this rank 2 example of sections that decay exponentially fast as we go very far in MR. Similarly, there is a filtration at the opposite end of R of sections that decay exponentially fast in the other direction. And so in particular, we can write any section of these line bundles L plus and L minus as some combination of, so this is a section of L minus, psi minus is a section of L minus, psi plus is a section of L plus. And formally, and we can write it formally like this, where psi is a section of E over L plus. And then we can define a locus, the locus where this holomorphic function f is 0, which is the locus on C star that supports bound states. So it's basically the locus where if you sit there and follow sections in both directions, they decay both as m goes to plus infinity and as m goes to minus infinity. So we call these bound states. I mean, they're it's not really a state in the bundle E, but it's just that if you restrict that locus on C star, you get you basically get these states that decay exponentially fast. And let me remark that in a classic paper, Hitchin used a similar method to encode SU2 monopoles on R3 in terms of a spectral curve on its space of lines. So the idea of Hitchin is that if you have a monopole and you want to use the Cohomology equation to scatter things, you can do so, and then you can keep track where the scattering problem has bound states, and this will carve out a curve in T of S2, which is the space of lines of R3. In our case, we only have one direction, which is R, so we're going to simply carve out points in C stars. Again, a codimension one locus where we have bound states. And the claim that then I make is that this locus here basically tells you at which points you have to glue your C stars to get what is the complex K-theory variety of P1. This means that we can reconstruct the complex equivariant K-theory of P1 from the spectral data of the Berry connection in a very similar spirit of what Hitchin did in this classic paper. So this spectral data that we call twistorial in the paper, but basically it just means that we can scatter along all the lines that we have available, not many in this case, and encode the monopole in terms of its bound states. So there is, here, just to give you a cartoon, maybe we have this locus x1 x equals to 1 where the bound states exist, and this is precisely the locus to the right of this image where the two copies of C are glued in order to get the equivariant complex K-theory variety. So let me mention that it is expected that this kind of spectral data is sufficient to reconstruct the monopole solution, but I don't think that has been fully proven in the mathematical literature. In any case, it's some spectral data for periodic monopoles that also exist. In the doubly periodic case, these sort of things have been studied very concretely. So I'm already out of time. Let me quickly tell you some conclusions and further directions. So to sum up, I claim that different kinds of spectral data for Berry connections of two theories that flow to a sigma model with target X encode a quantization via brane amplitudes of a spectral variety related to the action of a pure Coulomb branch algebra on the quantum equivariant cohomology of X. And moreover, another kind of spectral data knows another kind of cohomology or generalized cohomology theory, which is the complex equivariant K-theory of X. Now, in the conformal limit, we obtain verifiable difference equations for vortex partition functions and hemisphere partition functions, which is nice. Now, there should be a Riemann-Hilbert correspondence between these two kinds of spectral data that is being elaborated by Konstevich and Zolbermann. And in my opinion, the connection to cohomology remains to be investigated. I haven't seen statements so far that mentions relation between this kind of spectral data and cohomology theories in case that a Berry connection comes from a physical theory. And finally, all of these statements can be lifted to 3D, where spectral data for doubly periodic monopoles now arising from physics should be related to the quantum K-theory of X and the elliptic cohomology. So if you lift this setup up one dimension, you should get, again, one interplay like this, but where now the quantum equivariant cohomology becomes quantum equivariant K-theory, and complex equivariant K-theory becomes elliptic cohomology. And yeah, I think I'll stop here, and I thank you very much for your attention.
Thank you. Any questions?
Yes.
Please.
So when you say that you can recover the equivariant elliptic cohomology of X, what kind of object is that for you? Is it a ring? In the context I'm familiar with, it ends up being a sheath.
Yeah, I mean, it's a ring, and we recover the spectrum of the ring. Yeah. I mean, I haven't talked. Yeah. Yes.
Okay.
I mean,
so for you, it's a ring.
Yeah. In this 2D case, where the relevant thing is complex equivariant K-theory, is indeed we can recover what we call the complex equivariant K-theory variety, which is just the spectrum of a ring. So we recover the ring. Yeah. I
see. So have you tried this in examples in the elliptic case? Like, what do you get for like P1 or something?
So I haven't personally looked at the 3D case now. Like this is just mentioned here in the future directions. So I haven't personally tried any example. I think Dan has a little bit more experience with elliptic cohomology examples. But yes, personally, well, we have been developing this 2D setup, and some of the examples we had, I've mentioned.
Okay, thank you.
Any other question?
Do you
to that point? Oh, sorry.
Oh, go ahead.
I was just going to comment on the last question. I think the spectral data, the way that we build the spectral data for 3D is pretty similar to what Andrea outlined for 2D, but you sort of consider the scattering problem for the buried connection on like R times the elliptic curve, and like sort of similar types of considerations tell you to like glue copies of the elliptic curves at certain loci. So in that way, it's sort of similar to, it matches onto the description of like elliptic cohomology, equivariant elliptic cohomology varieties for like the GKM case or something. This is a similar sort of description as the K-theory that Andrea outlined in 2D.
Okay, so you get a variety.
It's not so different. Yeah, exactly, yeah. And you sort of show that ground states form, I guess you don't have functions in elliptic case, right? You have line bundles, and you show that just like in the 2D case, you have boundary conditions, but now they generate line bundles over this elliptic cohomology variety.
Okay, thank you.
In relation to your last bullet point here, do you expect a connection between the quantum K-theory and elliptic cohomology? And elliptic cohomology is without the quantum. So that's, I guess, the question is, you have a quantum on one side and somehow you generalize things in such a way that maybe quantum on one side is elliptic on the other side without the quantum.
Yeah, I mean, I think that's that's right. But the intuition is that whatever on one side, like complex equivariant K-theory or elliptic cohomology, really depends from viewing the system as, effectively you have a quantum mechanics that describes maps from either a circle or an elliptic curve to some target. And there is no quantum there. Like the quantum, the cohomology that one uses to play these buried connection games is the one that basically that squares to rotations of circles or cycles in the elliptic cohomology case, and it's basically you're morally looking at the cohomology of the loop space or the cohomology of maps from the elliptic curve to the target, and there really is no quantum, but the quantum does exist on the previous side because naturally, yes. what the supercharges compute is basically that. Yes.
So if you take the P1, your example P1,
yeah,
we understand, right? We understand the spectral curve, we understand the ring also, all this, the superpotential, we understand that.
yeah.
So should I be looking at what? Elliptic cohomology of what? The K-theory of P1 should be related to what, like more concretely?
Like, yeah, what I claim here in this talk is that, I mean, the relation is a subtle word, but it's like that the different kind of spectral data for the Berry connections or basically encode the rings that are the quantum equivariant cohomology of P1 and the complex K-theory of P1. And
I should also add that for P1, the quantum K-theory and quantum cohomology are very similar, very, very similar. So it's like the rings, it's hard to distinguish them unless you make the variables somehow slightly different.
Right.
So they are isomorphic as rings, but it doesn't, of course, generalize to other spaces.
Yeah, it's I agree that it's a bit of a degenerate example, but yeah, in more general cases, we expect to extract these two rings that may in general not be related or too similar to each other.
Okay. All right, thank you.
Thanks.
Let me jump in for just a minute to say I really enjoyed the talk, but I've also got to get out of here in a few minutes. So let me thank you for the talk and sorry, wave goodbye.
Yeah, thanks. Goodbye, everyone, and yeah, thanks for hosting us.
Let's
Everyone else
thank
can feel
Andrea
free
again.
to stay. I just have to get out of here.
Okay.
Yeah, if there's no more question, we can thank Andrea again. And I will stop recording.